Let's recap from the quiz. The coefficient of x gives the initial slope, which is the direction of the initial velocity vector v0. If we launch at an angle theta above the horizontal, tan theta equals vy0 over vx0. The coefficient of x squared is minus g over 2 vx0 squared. The minus sign tells us that the parabola curves downwards. Well, things fall down. Also, it tells us that if vx is large, it doesn't curve down so much. Let's now use the trajectory to interpret our equations for x of t and y of t. Equation Roman 1 says that x increases at a constant rate. Equal increase in x in equal times. So the velocity component in the x direction doesn't change. Remember, we're neglecting air resistance. In equation 2, the first term says that the projectile starts going upwards, well, if vy0 is positive. The second term tells us that the upwards component of v decreases, that is, it's accelerating downwards. Of course, if vy0 were less than 0, if we throw it downwards, then it just keeps going faster and faster with time in the downwards direction. This curve in space, y as a parabolic function of x, is the trajectory for projectiles near the Earth's surface if air resistance is negligible. When gravity is the only non-negligible force acting, we say an object is in free fall. To get astronauts used to free fall, NASA has a plane, it's nicknamed the Vomit Comet, that flies along such a parabola for about 25 seconds. The humans inside travel along the same parabola, with gravity the only force acting on them. They seem to be floating. In fact, they are accelerating downwards at 9.8 metres per second, but so is the plane, so that they don't accelerate with respect to the plane. More about free fall when we look at gravity. Here's another important question. How far does a projectile travel? How does its range depend on the magnitude and the direction of the initial velocity? Let's do an experiment first. These projectiles are drops of water. They're small, so the approximation that the air resistance is negligible is a rather crude one. Let's see how the range depends on angle. If I make the angle very small, then they're not in the air for very long, so even though they've got a large x velocity, they don't travel very far. If I make the angle large, close to vertical, then they're in the air for a long time, but they don't travel very far because they've got a small x component of velocity. So maximum range will be some angle between 90 degrees and 0. Our object, find out what it is. Here's the equation for the trajectory. To find the range r, we want to know when it hits the ground, when y equals 0. So let's substitute 0 for y and r for x. We cancel r and we move the second term to the left-hand side, then cancel vx0. Then we rearrange to have an expression for the range r. Well, it's no surprise that the range is proportional to vx0. It's also proportional to vy0 because the faster you go up, the longer you stay up. Next, we substitute for the components of v0. And we can simplify that because of a trigonometric identity. Sine 2 theta equals 2 sine theta times cos theta. So here's our expression for the range. Note that it goes as the square of the takeoff speed. Twice as fast takes you 4 times as far. Why squared? Well, first, more v0 gives it more x velocity. But it also gives it more y velocity, which keeps it above the ground longer. So, what angle gives maximum range? The maximum value of sine 2 theta is 1, which occurs when theta equals 45 degrees. Well, that's roughly in agreement with our experiment. Only roughly because here the air resistance is small, but not 0. Well, that's enough material to do a range of problems on projectiles, so let's do the next quiz before we return to look at circular motion.